We found a nice formula for information, which is that the information is equal to log base 2 of 1 over the probability of an event, which is equal to negative log base 2 of the probability. Okay. Now, the issue with this formula is that a lot of the times you're not just doing an event one time, right? An event isn't just happening once. You're looking to find the average, you're looking to quantify potentially the average surprise over all possible outcomes, right? So like this information here allows us, okay, for one roll of the die when I get a 4, this is my information gain. But I want to know on average when I roll a die, what is the surprise I'm getting, right? And this will account for all the possible options. So getting a 1, 2, 3. I don't just want for a specific option, I want an average, right? So that is what entropy is. So entropy, okay, is the expected value, which is the same as an average, expected value of information. Okay, the entropy is the expected value of information or surprise due to of a random variable x. So the way we'll take it is we'll take this information and we'll take this information, take the expected value of it to get the entropy. So the entropy of a random variable x, all right, let's say x has the following outcomes, x1 all the way up until xn, so n possible outcomes, and the probabilities associated with those events are p1 all the way through pn. We basically, as we normally do in expected values, we take a weighted average of all the possible informations. So we're going to take, okay, what's the information from, let's first figure out what's the information from the first event happening, right? That's going to be negative log base 2 of the first probability, right? The first event happening, so P1. Okay, but we need to actually weight it by its probability. So that's where the weighted average comes in. We multiply by P1 in front, right? Then we can do the next term, which is going to be, right, plus P2. So weight the second event happening. If let's say there's a dice roll, this would be rolling a 2, right? Weight that with its information. So weight the information of that event with its probability, right? And so on. We continue all the way up until we get plus dot 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 plus Pn times negative log base 2 of Pn. All right, this is entropy, right? Another way it's commonly written is entropy is the expected value of information, right? Which is equal to the sum over all x of p of x times log base 2 of p of x. Right, where x are your possible outcomes. So you sum over all of the possible outcomes, sum the information multiplied by the weight of that probability, right? And this ensures that, okay, let's say I have an event in here, like P3, right? It has a very high information. So this value is high for P3. But it doesn't happen that often, right? So you have to like balance those two, right? Even if maybe one possible outcome has a lot of information, but it doesn't happen a lot, then the average information for doing the event will not be affected by that one outcome a lot, right? So now we understand that entropy is the expected value of information. There's a nice way of thinking about information is, let's say, so the expected value of information is equivalent to the average number of questions you have to ask to determine an outcome. Okay, so the information, in a sense, information in general, is related to questions you need to ask. And we'll see why. Okay, so here's the scenario. Someone rolls a 4-sided die. So you have 4-sided die. Let's do this color. 1, 2, 3, 4. Your goal is to ask yes or no questions, okay, to figure out what the roll was. Whether it was a 1, a 2, a 3, or a 4. So how do you do that? What's the optimal way? And we're going to see that the number of questions you have to poke at to get the information you need is exactly going to be the same as the number of is going to be the exact same as the entropy of the person who rolled the dice. So when the person rolled the dice, that event has some entropy, which is the average information. Now the number of questions you're going to ask is going to exactly have to equal that to get that information out. So that's why those two need to be equal. Okay? So let's see. Let's visualize it with a tree, right? The smart strategy is to ask yes or no questions that split the the playing field into two. So assume these all happen with equal chance. So let's write the probabilities underneath. The probability of a 1 happening is 0.25, 2 is 0.25, 3 is 0.25, and 4 is 0.25. So you start, right? Let's make a tree. So the possible options are 1, 2, 3, or 4, right? Let's say you ask a question to split this into two categories. What could your question be? A nice question, a very simple question would be, is your roll, is it less than 3? Right? If the answer is yes, it is less than 3, then we've gotten down to two options. If the answer is no, then we've split down into two options again. Then at each one of these branches, we can just ask one more follow-up question, as if we're between 1 and 2, we can basically ask, is it 1? And if the answer is yes, then we know it's going to be 1. If the answer is no, it's going to be 2. Simple, right? Same way here, we can say, okay, a little bit redundant, but oops. Is it 3? Yes or no? If it's 3, boom. If it's not, boom. Okay, so let's go through each of these possible. We want to find. So it looks like, right, on average, we're asking two questions. But here's how we can quantify that. Or you can say, okay, along this route, right, how many questions did I ask? I asked 2 questions, correct? And then what is the probability of the thing that I rolled, right? This is 2 questions asked. So let's do the questions first. 2 questions asked. This way was 2 questions. This way was 2 questions, and this way was also 2 questions, right? So all of these here, we've asked 2 questions, right? Now, with these 2 questions in this scenario, we uncovered a 1, correct? We got that it was a 1. Now, what's the probability of a 1 occurring, right? The probability of a 1 occurring, we said, was 0.25. Okay? Same here. The probability of a 2 occurring is 0.25. Probability of a 3 occurring is 0.25. And probability of 4 is also 0.25. Okay? So based on our information definition, we should be able to calculate the information associated with rolling a 1. And we can, right? We can do information equals a negative log of the probability, with the probability is 0.25, so 1/4, log base 2, right? 2 to the power of negative 2 equals 1/4, so this whole thing becomes negative 2, and then negative 2 becomes positive 2. So the information here is 2. And notice how the information for each one of these possible events is exactly equal to the number of questions we have to ask to determine that event, right? So that's information shown here. Now what entropy says is that, okay, there's a situation, not in this case, but sometimes these probabilities may not be as likely. So what we're going to do is we're going to take the information for each event and multiply it by its probability and add those all up, right? So in a situation where potentially to get a 4, you might have to ask an extra question. It'll turn into 3 questions, information of 3. The probability might be a little bit lower, of probably to 1.15 or something like that. And so that will affect the average questions you need to ask. But in general, in this case, right, we're going to multiply, okay, the questions needed to ask to get a 1 out are 2. The probability of that is 0.25. Plus, probability for getting a 2 is 0.25. Questions is 2. Right? So we're basically doing this times this for all of those scenarios. And you can see that's obviously going to come out to 2, which is the average number of questions we need to ask, which is the entropy of rolling of this event occurring. So that's a very nice, visual intuition for connecting all of these concepts. Okay, the last sort of important, I guess, interpretation of entropy is it's related to uncertainty of X, right? So if you have an event X and h of X is high, so h of X is large, right? that means that X is uncertain. So we have high uncertainty. We don't know what's going on there. Why? Because we need, remember, h of X, entropies can be interpreted as the number of questions asked to figure out what's going on with X. And so if we have to ask a lot of questions, if entropy is large, then of course we have high uncertainty, right? High uncertainty in X. Okay? Let's think of an example. Let's just, think of a quick example. If we have two scenarios, okay? We're flipping a coin in both scenarios, but the coins are different. In this leftmost scenario, the probability of heads is 0.5 and the probability of tails is 0.5. Why am I doing heads and false? Heads and tails. Let me just make a new scenario. Okay. So, for this left scenario, we have heads and tails, equal chance of each. And for this right scenario, we have heads and tails, but we have a biased coin. Let's say it's 0.9 chance of getting heads and 0.1 probability of getting tails. Okay. Which would you expect to have more entropy? There's many ways of figuring this out. First way, we can think of entropy as uncertainty. Which event is more uncertain? Right? Which event has a higher confusingness, randomness, right? Clearly this event is going to have a much higher uncertainty, right? Because here, if I asked you to guess what heads would be, you would be very comfortable with your guess of heads here. But here, you can't choose a guess like heads, okay, 50% chance. It's only 50% chance. Here, you have a 90% chance, right? So you would expect here, this one to have high entropy. Oh, sorry. This one to have low entropy. Whoops. This one to have low entropy. And this one should have high entropy. Right? The other way is you can think about in terms of questions asked. So here it's a little bit tricky because, again, it's two outcomes, so you have to ask. Technically, you have to ask one question always. But on average, let's calculate the average number of questions asked, right? There's a better split. So the entropy here, right, will be probability times, so probability of some I times log of probability I, sum over all i's. Take the negative of it, right? So it's going to be, let's apply the formula here, negative 1/2 log base 2 of 1/2 minus 1/2 log base 2 of 1/2. And we've shown already that the entropy of one fair coin flip is 1 bit. Correct? Now, if we do it for the biased coin, the unfair coin, the entropy is going to be negative 0.9 log of 0.9 minus 0.1 log of 0.1. I'm going to quickly put that into a calculator. It should hopefully be less than 1 bit. It's coming out to 0.47 bits. Okay, so what we're showing is that the overall event as a whole this is a much more certain event. This is a much more uncertain event. Okay, so that's kind of the introduction to entropy. Hopefully you also watched the information video, and hopefully now you're getting a good idea of what we're talking about here, what we mean when we say entropy, and kind of why this is important. We'll talk about applications to compression and encoding in a future video, and then we'll also talk about more specific types of entropy. Like there's conditional entropy, joint entropy, then we have the ideas of mutual information and cross entropy, KL divergence. We'll touch on all of those in a future video. All right, see you then.